But the water molecules in a glass of warm water move around many times more rapidly and have much more thermal energy. When you put ice into warm water, the water gives up some of its thermal energy to the ice. The flow of thermal energy from one place to another is called heat. Heat always flows from something warmer to something colder. When heat is added to a substance, its molecules move faster. When heat is taken away, the molecules slow down.
Heat energy can be converted into other forms of energy, and other forms of energy can be converted into heat energy. In a power plant, heat can turn water into steam that turns turbines. The mechanical energy of turbines, in turn, can be converted to electrical energy. And electrical energy can be converted to heat, as when the coils on this electric burner get red hot. Another illustration of how different forms of energy can be converted to heat energy is provided by this pad, which contains special heat-sensitive chemicals that change color. When you put your hand on the pad, it leaves a slight impression caused by the heat in your skin. If you then rub your hands together vigorously, this mechanical energy causes friction that excites the molecules in your skin, making your hands hotter. And if you place a hand on the pad again, it will leave a much brighter impression.
In addition to making their molecules get more excited, adding heat causes most substances to change in other ways.
Are you watching this?
A simple experiment shows how.
Yeah.
This metal ball was designed so that it just fits through this ring. But observe what happens when this student heats the ball. Any experiment involving fire should be done under the supervision of a teacher or other adult.
He's not really watching.
After the ball is heated, it no longer fits because the excited molecules in the ball have moved farther apart, causing it to expand. Now look at what happens when she puts the ball into some cold water to cool it off. When most substances lose heat, they contract because their molecules are less excited and move closer together. Builders and engineers have to take into account that steel, concrete, and other building materials expand when heated and contract when they lose heat. Bridges, for example, have expansion joints that give the steel and concrete sections room to expand in the hot summer months. Water is an important exception to how substances expand and contract when heated and cooled. When water freezes and becomes solid ice, it expands rather than contracts because of the special way water molecules and ice bond to each other.
As they become hotter or cooler, gases and most liquids other than water expand and contract much more than solids. The base of this thermometer contains liquid alcohol. When this liquid is heated by putting it into hot water, its molecules become more excited and move farther apart. The alcohol expands and rises up a very thin tube that runs the length of the thermometer. When it is cooled, the alcohol contracts as its molecules become less active. As it contracts, the alcohol falls down the tube. A scale on the tube marks the temperature. Some thermometers use the Celsius scale, which is based on the fact that water always boils and freezes at the same temperatures when the pressure in the atmosphere is the same. At sea level pressure, 100 degrees Celsius marks the boiling point of water. And 0 degrees Celsius marks the temperature at which water freezes. Other thermometers use a different scale. With a Fahrenheit thermometer, the freezing point of water is 32 degrees Fahrenheit. And the boiling point is 212 degrees. The numbers of the two scales are different, but the temperatures they mark are the same.
No matter what kind of scale it has, a thermometer measures temperature, not heat. Temperature and heat are different in important ways. Temperature is is to measure how fast the molecules in the substance are, on average, moving. Measure the temperature in a tub of warm water. Then fill a cup with water from the tub and measure the temperature of this water. The two temperatures will be the same. This is because the molecules of water in the cup are moving around, on average, as much as the molecules of water in the tub. But the tub has much more thermal energy because it has many times the number of water molecules as the cup does. Because it has so much more thermal energy, more heat can flow from the water in the tub than the water in the cup. The water in the tub, for instance, could quickly melt a pitcher of ice.
Which do you think has a higher temperature? The flame of a candle or a radiator? Which has more heat? If you wish, you may stop the video now to discuss that question.
Which one?
Otherwise, the program will resume in 10
Here?
seconds.
You're here. Anyone else? Down, down.
Peter.
The flame of a candle and a radiator show the differences between heat and temperature. The flame has a much higher temperature, but the radiator has much more thermal energy because it has more molecules than the flame. It can give off a great deal more heat, enough heat, in fact, to warm a whole room. While temperature is measured in degrees, heat is measured in units called calories. A calorie is the amount of heat it takes to raise the temperature of 1 gram of water 1 degree Celsius. The value of any kind of fuel can be measured by how much heat it gives off when it burns. A gram of gasoline gives off about 11,500 calories. A gram of soft coal gives off 6,000 calories. And a gram of oak gives off 4,000 calories.
We saw earlier that heat always flows from something hotter to something colder. There are different ways that this happens. An experiment shows one way that heat is transferred from one place to another. Here, a student puts some wax on the heads of 3 tacks. He then sticks the tacks so that they are spaced evenly apart along a steel rod. A Bunsen burner then heats the end of the rod. In a few minutes, the heat from the burner is transferred from one end of the rod to the other. The wax melts, and the tacks fall off, one after the other. But how does this happen? The steel rod is a solid. The molecules that make up the end of the rod vibrate more quickly when heated. But the molecules can't move from one end of the rod to the other.
Pool provides a hint about what happens with the molecules of the rod. When someone makes a shot, energy is transferred from the player's arm to the white cue ball. When the cue ball hits the second ball, it transfers its energy to the other ball. Often the cue ball hits one ball that in turn transfers energy to still another ball. Something similar happens with the molecules that make up the steel rod. As the molecules at one end are heated, they speed up and vibrate more. These molecules transfer energy to the molecules next to them, which become excited and move more rapidly. These molecules, in turn, excite the molecules next to them, and so on. In this way, heat energy is passed on from molecule to molecule, the whole length of the rod. This type of transfer of heat is called conduction. Conduction occurs when heat energy flows from one molecule to another as they collide.
Different substances do not conduct heat equally well. These spokes are made of different kinds of metal, including copper, aluminum, steel, and iron. Here, a student has attached a tack to the end of each spoke. He then heats the hub so that each spoke gets an equal amount of heat.
Where is
the wax melts and the tack falls off the copper spoke before hitting the others. The next tack to fall is from the aluminum spoke.
Heat doesn't conduct easily through the plastic to the colder air around the cup.
Here is a question to think about or discuss. How do materials that are good insulators cut down on the amount of energy it takes to heat a home? You may stop the video now.
Alright, what do you think?
Otherwise, the program will resume in 10 seconds.
What do you think? How do insulators cut down on energy?
They use wood.
Yeah, but if you wrap your house in a good insulator, it prevents heat from escaping.
Insulators are used to help conserve heat in houses and save energy. This insulation is made of fiberglass, which conducts heat poorly. In an attic, it helps prevent heat from escaping through the roof. Certain kinds of windows also help conserve heat. This cutaway model shows how some windows have a layer of air between two layers of glass. Air and other gases are poor conductors. The molecules